Hey everybody, welcome back. In today's econometrics video, we're going to look at a super simple treatment effects estimation using a difference in difference model. We'll look at the assumptions and the data necessary for it to be valid. We'll break down a simple numerical example, and then we'll look at a regression estimation in Stata. So let's take a look. So let's get into the difference in difference estimator. What are we talking about here? So imagine a situation. Suppose we wish to estimate the impact of some treatment on a given outcome over time. So lots of different examples we can think of. Just to pick one, imagine we want to think about the impact of access to tutoring services on students' grade point averages. Okay. So the first thing we might think of is to say, well, let's just calculate the average GPA of all the people that had access to tutoring relative to the average GPA of all the people that didn't, so the treatment group versus the control group, and the difference between those is the added benefit or the effect of access to tutoring or the treatment effect. Generally, we're not going to be able to do that, right? Because what if people that took advantage of the tutoring already had better grades, right? That would be kind of a selection bias scenario. So unless we know that we're starting with from a level playing field, the gap, the difference between outcomes in the treated versus the control group after treatment isn't necessarily going to accurately capture the effect of treatment. So what would we actually need to do, and hence the name of our topic here, we want to look at the difference in the changes or the difference in the paths over time from pre-treatment to post-treatment across the two different groups, right? So we're going to end up with this little 2x2 matrix of outcomes. Where did each group start the pre-treatment averages versus where did the two groups end up the post-treatment averages of those who received treatment versus those that didn't? That, in effect, is the difference in difference estimator in its most basic form. Okay, so now for some notation, right? So we can actually write down the model. Assume that the event or the treatment in question, so in our example, when did the tutoring center open, right? When did access to treatment occur? Happens between period 1 and period 2. So we're assuming we have panel data with only two periods. Period 1 is pre-treatment, period 2 is post-treatment. And just to pick some notation, we'll denote type B as the treated group, type A as the control group. So type B received the treatment, they're in the tutoring center. Type A didn't. Okay, so what we're trying to find, the effect of treatment on our outcome of interest, our Y variable, which in our case is our grade point average, we will denote that as this delta sub DD. So as we said, what we're trying to find is the difference in outcomes between the groups after treatment versus before treatment. So it's going to be structured like this. So our delta DD, our treatment effect, is going to be our average outcome in period 2 for the treatment group. So Y bar sub B2 relative to the post-treatment average outcome for the non-treated, for the control group. So Y bar sub A2 relative to the gap that already existed between the groups before treatment in period 1. Right? So here is our difference across types, the A versus B, control versus treated, after treatment relative to the difference across types before treatment. So that change in the path of the two groups between period 1 and period 2, again, conceptually, it should be clear that that is going to be the effect of treatment, assuming, of course, that no other event of consequence occurred in between period 1 and period 2. So we'll get to the assumptions momentarily. So again, this is going to be our ATE, our average treatment effect. And we can rearrange those terms in the calculation that we just saw to get another version of it that also makes some sense, right? So it's going to be the pathway for the treated group between period 1 and period 2, right? How much does their GPA increase between period 1 and period 2 versus that path for the control group? How much did their GPA change from period 1 to period 2? Again, the gap, the difference between those is again going to be that treatment effect. So treatment impact on the treated. So how did things change pre to post treatment versus how did things change for the control group over that same time period? We call it the treatment impact, even though by definition they didn't have access to the treatment, but it was over that same time period. So again, we're just rearranging the terms, but another way to think about how to estimate this effect. So like we said, we get this little 2x2 matrix or table of outcomes of interest, and it's pre versus post, control versus treatment. So those are the four terms that we're always going to be playing with, right? And again, when we put those together, we have these two different kind of dimensions that we're looking at to calculate the estimated treatment effect. So the top version of it here, the first one we looked at, it's post-treatment differences between groups. So that would be the difference here between A and B post-treatment relative to the difference here, the difference between A and B pre-treatment. And then the second version of it, right? Again, this would be the vertical on our little table here. So how did things change from period 1 to period 2 if you're in the treatment group versus how did things change period 1 to period 2 if you're in the control group? The numerical calculation is going to be the same, just a slightly different way to think about it. Okay, so another very important ingredient here to both kind of the visual aspect of what we're going to estimate as well as the OLS calculation is going to be this idea of a counterfactual treatment group outcome. And the whole idea here is to answer the question, right? What is the difference between outcomes in the treatment group with treatment versus without treatment? And we don't have access to that information, right? We can only see the control group and the treatment group with and without treatment. So we want to say, well, if we took the same people that had the treatment and we didn't give it to them, where would they be? So what would the treatment group outcome be post-treatment if treatment hadn't occurred? We don't have access to that information, so therefore it is a counterfactual. Here's where the assumptions come into play, right? So by assumption, we're going to say it follows the same path as the control group. So the growth rate of the outcome variable between period 1 and period 2 that was experienced by the control group, we're going to say, well, that's what would have been experienced by the treatment group had they not been having access to treatment. So this gives us another way, I think a more satisfying way of calculating that same treatment effect that we talked about, right? So the counterfactual outcome, the period 2 outcome for the treatment group had treatment not occurred, will be where they started, right? So the average outcome for group B in period 1 plus the same value change that was experienced by the control group. So the difference between period 2 and period 1 for that control group. In other words, we're applying the same slope to that path over time from one group to the other. So the actual outcome that was experienced by the treatment group, Y bar sub B2, right, after treatment, minus what our counterfactual is, their starting point plus the growth experienced by the control group, that gap will be another way to get our average treatment effect. So we can add effectively a third column here to our original 2x2 outcomes. And the third column is our assumptions, right? The counterfactual path of the treatment group. So the assumption is that, right, we're starting in the same place, but rather than getting to where they actually end up after experiencing treatment, let's say they experience the same growth as the control group. So this term here, YA2 minus YA1, that's applying that same slope term. So this is where they would have ended up with a parallel trend to the control group had treatment not occurred, and this is where they actually end up. So the gap between those two things is going to be another way to view our treatment effect, right? So the actual outcome, YB2 minus the counterfactual, YB1 plus the growth of the control group, rearrange those terms, and we're right back where we started, right? So it's always the same four ingredients, but now we have three ways of calculating and thinking about this difference in difference treatment estimator. So now, from my point of view, probably the most interesting way to look at this is simply the visual, right? So if we plot out essentially those three paths, the three columns in that last little chart, we'll once again be able to isolate this difference in difference effect. So on the vertical axis, we're simply measuring our outcome variable. So imagine this is grade point average, right? And then tracking time along the horizontal, where we only have two periods of interest, period 1 and period 2. And then somewhere in between period 1 and period 2 is when treatment occurred. Okay. So that's that vertical red line. Okay. So let's start with the control group path, right? So they're starting off at Y bar A1 here, and we're imagining, again, it could slope either way. It could be flat. We don't know. It depends on the data. But imagine that over time, our output variable grows, even though this is the control group and they're not having access to treatment. So they just have a positive trend effect. All right. Then we have the actual path of the treatment group. They started here in Y bar B1. And again, it doesn't have to be this way, but we're imagining the treatment group started with a higher level, and they also had a positive trend. And they end up here at their post-treatment average, Y bar sub B2. And again, the fact that that line is steeper indicates that having access to treatment accelerated the growth from period 1 to period 2 versus the control group path. The rate at which it's accelerating, that's the treatment effect, right? The difference in those slopes. And that's what that counterfactual is able to capture. So this dashed line here, that's the counterfactual. So it's starting at the original point for the treatment group, but it grows at the rate of the control group path. So it's a parallel line to the control group path. And that distance here between where the treatment group actually ends up versus where they would have ended up if they grew at the same rate as the control group, that is our treatment effect. That's the delta sub DD. That's the difference in the differences. Okay. So when you're actually playing with data, it's really, really useful both for you, the researcher, and for your audience, right? To be able to plot out a little path like this. So, and all it takes really is the calculation of four different numbers, essentially, the starting points and ending points of your two groups, and then arranged appropriately with the addition of that parallel line for the counterfactual. Okay. So again, just to really hammer this home, in order for this to be an identified model, in other words, to give us an unbiased estimate of that average treatment effect, first and foremost, we have to be able to rely on that parallel trend assumption, right? So we must assume that the trends over time of our outcome or our dependent variable would be identical between the treated and the non-treated group, right? Prior to treatment and with the innovation of treatment. Okay. So the way we're doing it here, we're not controlling for any other factors, right? And we're assuming that the only reason that the slopes diverge is because of treatment. So that's a pretty strong assumption. But if it's true, Then we get our identification, right? Any difference in those trends, any difference in the post-treatment outcome can be reliably attributed to the treatment effect, which is what we're trying to estimate here. Okay, so last thing before we actually look at some numbers here, we can calculate it as we've set it up here without actually running a regression, without actually doing any OLS estimation, just by looking at the differences, right, in those possible outcomes. But it turns out we can also estimate this really simply, and it'll also give us a launching pad for more complicated models with an OLS estimation. So difference in differences in OLS simply requires two dummy variables. A dummy variable to identify which observations are in the treated group versus the control. So that's what we'll call D sub treat I. So that'll take on the value 1 if observation I is in the treatment group. So for everybody that took advantage of whatever tutoring services in our little example, they're going to have the value 1. And then the other dummy variable is just a time indicator dummy variable, taking on the value 1 for each observation in period 2, the post-treatment period. So the combination of those two dummy variables and the interaction between those two will fully specify this difference in difference model. Right? So the estimation would be trying to predict our outcome variable as a function of treatment, time, and the combination of those two things. So think about this term here, this what we've denoted as delta DD. That is going to be our OLS estimate of the difference in difference treatment effect. By interacting these two dummy variables, we're getting exactly what we want, right? The impact of being in the treatment group after treatment. What is the added benefit, right, over and above being in that group originally, so the starting point, and the growth that occurs on average between the two groups, holding those constant, the added effect of being in the treatment group post-treatment is exactly what we want, the treatment effect. And it turns out, numerically, it'll be exactly the same as what we calculated as the difference in the differences of the means. Works out very nicely. Okay, so let's go ahead and look at some numbers. We'll break it down basically in a spreadsheet. Then we'll jump into Stata. Okay, so I've got a little example made up data set here just to play around with, where, again, we're imagining we're tracking students' grade point averages before access to tutoring and after. So our first two columns here are simply the panel identifiers, right? So student goes from 1 to 10. So we have a sample of 10 students, and they are sampled in period 1, and then again in period 2. And again, the assumption is access to treatment occurred between period 1 and period 2. So that's what we're trying to capture, right? So we have this repeated balanced panel here. And then we have our outcome variable, our GPA, and then the dummy variable, which is essentially our treatment indicator dummy variable. So taking on a value 1 if you're in the treatment group, if you took advantage of tutoring. And then we also have our time dummy variable that takes on the value 1 in period 2. So that's our post-treatment indicator. We're not going to worry about it for this example, but we also have, say, in a more realistic data set, you would also have a bunch of control variables. So here, study hours as a continuous control variable. So I have conveniently color-coded the data here, right? So in this first group here, we have our outcome variable for the treatment group before treatment, right? So looking over here, we see our little pre-populated 2x2 table, right? So this number here, 3.12, that is the average of the treated group before treatment. So it's in period 1, but treatment has occurred, right? So our post-treatment indicator is 0. Moving down, this next group is still in the pre-treatment phase in period 1, but this is in the control group. So the treatment indicator is equal to 0. So this is control group, pre-treatment. And now this last observations, we are in period 2. Here, this is the treatment group in period 2. So that would be our Y bar 2B, right? So average GPA 3.3 after treatment for those in the treatment group. And then the last group down here, period 2 post-treatment, but in the control group, treatment indicator equals 0. So we've got all the ingredients we need right there. But notice I've also pre-populated this counterfactual column. So the idea again is, what if we started at the same point? So this is for the treated group. So we're starting with that average GPA of 3.12, but instead of increasing all the way to what actually happened, 3.3, what if it increased by the same amount, right, the same slope over time as our control group? So our control group increased their GPA from period 1 to period 2 from 2.8 to 2.87. So they add that 0.07. So if the parallel trend holds, the counterfactual for the treatment group would be from 3.12 to 3.19. So keep that in mind. So now, with these 4 color-coded averages, again, we have everything we need to calculate the difference in difference. So let's do it piece by piece. So the difference between groups pre-treatment, right, we can calculate as Y bar period 1 group B minus Y bar period 1 group A. So we can see that those that eventually sought tutoring already had a GPA that was 0.32 units higher than those who didn't. What's the outcome after treatment? So here it's going to be calculated as our post-treatment for the treated minus the post-treatment for the control. And the fact that their GPA is higher by a greater margin after treatment tells us treatment had a positive effect. So our difference in differences is just going to be the 0.43 minus the 0.32. So the delta DD treatment effect estimation is 0.11, okay, which would be different than simply the difference in outcomes treated versus control, right? So we're controlling for where we started versus where we ended up. So the last piece of the puzzle here, we have the little visual. And so here, obviously, I just constructed this in sheets, right, using a simple line graph, but it gets the point across, right? So the same idea that we saw in the generic slide, right, actually turns out exactly the same, that our control group started at a lower point and grew at a slower path. And to pick out the treatment effect, we start at the initial point for the treated, and then we have our 2 slopes, the actual slope versus the counterfactual. The gap between them is the delta DD, right? The treatment effect. Okay, for our last trick, let's put this data into Stata, run the regression, and in a much quicker fashion, get that treatment effect. Okay, so we're simply going to copy and paste our raw data here into the data editor in Stata. So let's go ahead and just copy that, jump over to Stata, go to the data editor, paste it in. We'll take those variable names, and there we have it. So we've got our GPA, our treatment indicator, our time indicator dummy variable, and that's all we're going to need, right, for our simple construction here. So our regression is going to look something like this. We're going to regress our Y variable, GPA, and what we want is the estimated coefficient on the time dummy variable, our post-treatment indicator, and our treatment group indicator, that tutoring variable, and the interaction. And we can do that really simply by using the double interaction indicator in Stata, right? So we're going to take our treatment variable, tutoring, and then we go hashtag, double hashtag, and post. So that's going to give us all the different combinations, each dummy variable individually and the interaction term. And lo and behold, look at that. We get the OLS estimated coefficient on the interaction term is that 0.11, exactly what we knew it was going to be, and that is our average treatment effect. So the obvious benefit, aside from just efficiency in using the OLS approach, is we can also do inference, right? In this case, t-stat of 0.51, p-value well above 0.5, we don't find a significant effect, but again, I made up this data. We only had 20 observations, and there's all sorts of other issues to take into account here that we'll briefly look at. But we at least have that possibility of applying valid inference and hypothesis testing in a fairly simple way to that difference in difference estimation. But this also, once we have it here in Stata, now you want to be asking questions like, should I be including continuous control variables? Should I be using robust standard errors, clustered standard errors? Should I have fixed effects? All of those are great questions. We're not going to get into them in this video. This is just the simplest 2x2 starting point, but those are all kind of extensions to this model. So I'll put some references in the description for some nice textbooks, some nice articles that use this kind of classic methodology to take a look at. If you have any questions, put them in the comments. Otherwise, I hope this was helpful, and we'll see you next time. Thanks.